this. Today we are going to talk about golden rules of deep learning performance. So let me quickly move this. This is basically chapter 6 of our book called the Practical Deep Learning Book. So written along with Siddha Ganju and Meher Qasim. So since I've been working in machine learning for about 13, 14 years professionally, and more in the modern AI side of things since 2013. And during that journey, often platforms didn't exist. So you try to build your own things, whether it is on mobile phones, whether it is on IoT devices, whether it is, or like how to scale it up in the cloud. And during that journey, often it meant basically making mistakes and going through a rabbit hole of, by making mistakes, you learn more. And eventually when an abstraction comes in, you start to learn, and then you start to preach that, hey, don't do what I did and spent a month doing. Instead, do this and spend about 30 minutes and you will be golden there. So going through that, I started giving these lectures to engineers on how to build things practically, which kind of became this guide eventually, taking you through, from your basic training to how to maximize accuracy, maximize your hardware efficiency, scaling it up in the cloud, onto mobile phone devices, robots, and eventually into autonomous cars. But the whole point is how to do it practically, and when you do it, you then learn the theory. And so the two cool stories that I'll quickly share is that, the book ends the last page on basically how to build autonomous miniature cars. And the last page is basically the photograph of this thing, which says, if you have followed the book so far, then the next step would be to take it to RoboRace, which is this real, championship racing car, which can be run autonomously. And a team from Carnegie Mellon was basically following that chapter and building their own miniature cars. And 5 months later, they ended up being the first North American university to actually qualify and join this. So it's like students just took that page a little too seriously and went to the next level. The second story was that this book is written in Keras, right? We learned Keras, we wrote it with Keras and TensorFlow, and eventually the founder of Keras is reading it. So that's kind of like recursion. So that's where my sales pitch ends and my presentation begins. So, when you meet any data scientists and you ask them like, hey, what are you spending your most time on? Most of them will tell you that they are waiting for training to finish. It's kind of like the common, XKCD joke about asking software engineers, what are they spending time on? It's basically compiling, right? And it's a very real story to me personally, because that's what I do and what I did long time. So something very personal. In 2017, I was training something for a production piece to build a model for production, to put it in production. And I noticed that the more I was training, the more I was starting to lose weight. And there was this some weird correlation that the more I would train, the more I would lose weight. And it didn't make any sense. What was happening was, my office has a hallway where I can actually walk in a loop, and it takes me 2 minutes to walk. And what I did was, in my training program, I basically optimized it in such a way that every 2 minutes, it would print the results of where it has reached with its training. So I'd start the program, go on this walk for 2 minutes, come back and see on my screen that where have we reached in training. If not, then I keep walking and keep walking. And so basically my number of steps went from 8,000 steps to 15,000 steps per day. The more I would wait, the less I would weigh. And I think it's a very common story with many people who train AI models. So how do you solve this? For AI Camp, I actually went to a friend to ask, how do you make waiting for AI lesser? And this is the reply.
This is like common sense. The more GPUs you buy, the more money you save. That's right. The more GPUs you buy, the more money you save.
Makes sense. But, we can follow his advice, especially if your boss has really good budgets. But, like in real life, we all have painfully experienced what we want is not always what we can afford. But what if we could take the car on the left side tune it up, put some nitro boosters in it, maximize its efficiency, and get it to the same power and level of the car on the left and race it. So I think we'll transform the car on the right to the car on the left and try to get the maximum performance, maximum efficiency from your hardware, whatever you own already. And that's what the aim for this, today's meetup will be. The other thing I would say is that I'll throw away the research hat away and put the practical hat on. So if something cannot be done in 2 to 3 lines of code, then we won't discuss it. So we'll discuss things that a developer can do by taking like a boilerplate piece of code and adding line by line to it to maximize the performance, because that's what we do here at AICamp. All right, so just to put a level playing field, I'm guessing many of you have already know the term transfer learning. 95% of all AI training really happens with transfer learning, but just in case you don't, just a quick refresher. The idea is that, let's say if you want to pick a new instrument like this melodica on the right-hand side, and you want to start learning how to play a melodica, this will take, something like 3 months to become better at playing at this. But if you already knew how to play a piano, you can fine-tune your skills. You can transfer your skills and use it to play on melodica, which is like a very similar looking instrument. And that's essentially the idea of transfer learning. You take a data set that is similar to yours, on which a model has been previously trained, like ImageNet, and then fine-tune, transfer learn on this new data set that you might have, like hot dog, not hot dog, right? So behind the scenes, what really happens is you take a convolutional neural network. At the very end, you have the fully connected layers. You basically take a pair of scissors, cut the ending, which is basically more task-specific layers, specific to the task. You cut it, and then you replace it with new layers that you then tune to your task at hand. If you haven't done this, you can go to the GitHub link at the very bottom, and within the next 15 minutes, you'll have your own transfer learning program running in Google Colab. So easy peasy, but that's the very basic idea. So now that we are at the same idea that, hey, training is easy, how do you improve performance? So first, let's look at the biggest culprit of performance, and it is GPU starvation. So what happens is that you pick, when you start training a program, what's really happening behind the scenes is you pick data from files, you read it, you spin the hard disk, find where it starts, you start first loading it. Then when you load, let's say, images, you then start to resize the images because you want to use the full resolution. You then start to augment it, turn a little left, turn a little right, create on the CPU. Then once all this processing has done, you put it in batches, then you feed it to your GPU. So the GPU is waiting all this time. Now the GPU got it, it starts to go into the super performance mode, play with the data, train the batch, do the back propagation. And once it's done, the CPU is waiting all this time. And then it tells the CPU, okay, we are done with this, feed me the next batch. And that's where, if you notice this, the red parts are where, the black parts are where it is fully utilized, and the white parts are where it is totally idle. Waste of this expensive GPU and those cores and cores of Intel CPUs or maybe AMD CPUs you have already bought. So our real task here is how to reduce this starvation. Well, you need to be able to measure whenever you do something in life. So we need some tools of the trade. And the tools, I'll first start with this thing called the Tensorboard profiler, TensorFlow profiler. It's easily available within Tensorboard. You can just open it while calling the Tensorboard callback function. And the basic idea here is that when you open this, kind of like when you debug things, if you notice my screen clearly, it says that there is something here which is the CPU, and the CPU is getting occupied, great. And then this thing called the GPU 0, I had 4 GPUs on my machine, and this was GPU 0, it started to get occupied. And as a practitioner, you will basically say, whoa, this means that my GPU was empty all this time from this millisecond to about 100 milliseconds, waste of my GPU. Technically, these 100 milliseconds sound small, but it adds up eventually. So this is like a way where you can go on a timeline when you have already run a program and then dive into deeply of how your performance is really running, are you having your wasted cycles. I will say it is calling this is easy enough. You just have to start this profile underscore batch equal to 7 when you call Tensorboard. But maybe you want something more simpler. Maybe you just want something that runs on command line. You don't have to worry about it, not open in a browser. And if you want to do that, well, NVIDIA SMI is a tool you should just remember. That is NVIDIA's System Management Interface. It tells you some cool things. For example, how hot your machine is going in Celsius, the memory taken by your deep learning program, the power bill that you are going to get at the end of the month effectively with wattage. And more importantly for us, it is the GPU utilization, right? And you want this number to be as high as possible. So when you run this NVIDIA SMI on your command line, considering you have an NVIDIA GPU, it should just run. It will tell you at that point, at that millisecond, how much GPU was utilized. If you run it when you're not running a deep learning program, it will probably be 0. Maybe try it on your video games, maybe. But maybe if you want to run it every few milliseconds so that you can see over time how this is running, simply put watch minus n.5 before any command that you're writing. So what will happen is it will just keep refreshing and printing and showing how it is varying during the time your program is running. So if you have ginormous CPU cycles with blockages, you'll probably go down to 0 sometimes. So this is a really neat tool to have. So now that we are here, the way we will follow our optimization, I think we can go many ways, but I thought let's figure out how to prepare the data more optimally, how to read it optimally, how to augment it more optimally, how to train, and then do inference. And let's get started. So let's go with data preparation. The first thing is there are anti-patterns in how to read files, whether it is deep learning or whether it is other things. You don't want to have thousands of tiny files, and you don't want to have one ginormous 300 GB file too. Because if you have thousands of tiny files, the time it takes to go and seek to the starting of that file, especially if you have a magnetic hard disk, then try to read them one by one, will be just too much overhead. On the other hand, if you have one ginormous file, you won't be able to parallelly read multiple parts of the file optimally. So these are two anti-patterns. What might be a much better idea is how about we combine many of these tiny files into handful of large files. So my recommendation is that, hey, go and build files which are 100, 100, 100 MB each. Kind of, how you may download zip files, but they are divided in a very similar way. And this is actually really good if you have to download these files eventually someday, let's say from cloud storage. So this actually helps. And the way you store this is using something called TF record. TF record is the thing you want to store your data, which internally uses protocol buffers, and this will make things really efficient. So TF record is the thing that will help you. Secondly, you want to reduce the size of the input data. So for example, imagine I'm loading data from ImageNet or Coco. What I have to do is I have to first read the data, then I will resize it, right? And then go it for training. But like this resizing step is going to take my CPU cycles again and again, right? That's gonna be wasting a lot of cycles. So won't it be a much better idea that, hey, how about I read the files, do all my pre-processing like resizing, and save it as a TF record. And then next time, all I got to do is just start reading this TF record where my resizing is done, and all I have to do else is augmenting and then training. So anything that you find you are doing again and again, which can just be reduced, go for that. Finally, anytime you work on a new data set, you have to first go download it, read the documentation, figure out the format, write a proper Python program to read it in the proper way, which God knows how many inefficiencies you'll have and more. Won't it be better if somebody has already done all that work for you? So in under 5 lines, you can just get started running. And that's where TensorFlow data sets come in. This is literally less than 5 lines of code here. I'm showing, I import TensorFlow data sets and show the number of data sets available from ImageNet to Coco to whatever else. Tons of them are available. And let's say I've figured out, I want to pick ImageNet or CIFAR 100. I can just take this, split it in training, and then shuffle and batch it. And I already have a pretty high performant training pipeline. So use TFTS. That would be my recommendation to you. Bonus, if you want to be famous and you want your name to be splattered across internet, you should publish your own data set on TensorFlow dataset so others will start to cite your work. And suddenly you'll notice that people start to retweet to you more and more. So highly recommended idea. All right, so now that we know how to prepare data, we know how to save the data so that we can then do the data reading more efficiently. Let's see what we can do. So the one takeaway I want from the next few slides is use tf.data. That is the gateway to high performance training data pipelines. In the next few slides, I will show a program and then add one more line, one more line, one more line, one more line, till we have like the full program of how to have the full pipeline. So we'll just build on it. So here's the very basic piece of code where I read a TensorFlow record, TF record format files using tf.data. And then I do some shuffling. You want to shuffle, I repeat it, I run it through a couple of functions that I have, built myself, let's say, resize it, and then batch it for my training part of the pipeline, right? So code, don't worry about this, but the key part is that you want to use tf.data, right? So let's see what we can do. First, we can prefetch data. So as we saw in the very first time, the GPU is waiting for the CPU to finish giving it the data, and then the CPU is waiting for the GPU to finish computations. Won't it be nice that we just make them both asynchronous and not dependent on each other? So what we'll do is that we'll take the CPU, and whatever it generates, it just feeds it into a buffer, right? Feeds it into a queue and keeps feeding, feeding, feeding. And the GPU, it just starts reading it from the buffer instead of waiting for the CPU to feed it. So it's kind of like one person is just throwing away all the data it can at its maximum speed, and the other person is reading from this buffer at whatever maximum speed. So we kind of reduce the dependency between each other. I remember from my third year in undergraduate, this was deadlocks and resource utilization. I think dining philosopher's problem. We are solving that in one line. So dot prefetch is all you put into your last, that tf.data pipeline. You literally add dot prefetch and add a buffer size. That's a number you have to decide, but we'll come to that later. So single line, suddenly your program will get faster. Great. Next line, maybe that you don't want to waste all those multiple CPU cores you have bought, right? Why run it on just one core? So here what you can do is run this thing called num parallel calls, and this will effectively parallelize it on the number of CPUs you have. So definitely go for that. But why just parallelize it on why just parallelize it for processing? We can also parallelize reading data. For example, imagine your data was stored on, say, a cloud provider and you're reading, let's say, from S3. Or it's on disk. So you can also parallelize not just processing, but also reading. So that is done using something called as interleaving. And again, this can be done where you call num parallel calls, then just add a number at the end to decide how much to parallelize it. All right. Second, lastly, you want to sometimes what happens is, imagine that you have tons of tiny files of like 10 MB and then one gigantic file of 100 MB. And when you start reading them, what will happen is it will keep waiting for that 100 MB file to finish, and that's the straggler, right? And it will keep waiting for it to finish to go to the next thing. And then all these files, if they're small ones, get stopped reading because the straggler thread. So what you can instead do is say that, hey, I don't care about data being in the correct order. Just give me data as you can read it, so that I don't care for the order. And that makes sense because technically you usually shuffle data when you read it. So why have the order at all? So you just write a single line called turn deterministic ordering off. And you'll notice that in case you have a straggler, those problems will start getting away. Finally, the golden rule of computer science. use caching. So by saying dot cache, you can use in memory, or you can even build on disk caches also by using the dot cache. So the idea here being that you can start putting these lines in your code, whatever you have, and start noticing how your program was running before and how fast it starts to run. Some of them will help, some of them might not help as much, but they're just going to go in the positive direction usually. Now, one thing you might have noticed is all these slides that I had previously shown, you see these numbers like num parallel cos equal to 4. Why 4? Why not 5? Usually, it's up to the software engineer or the data scientist to play with these numbers and come up with an optimal value. What is the buffer size? All this stuff. And you can do that, but then you have to keep tinkering with it, right? So it runs optimally on your machine. Then you put it on a cloud provider, and suddenly the settings there will be different. Maybe there's a second program running in the background, and then the settings you currently have might not be the best ones because that other program is also taking CPU thread. It's a lot of experimenting. What you can instead do is simply run auto-tune. Auto-tune is originally it was built like a reinforcement learning mechanism where it learns as your program is running by changing the parameters. So wherever you have the number like number of parallel calls, buffer size, instead of writing a number, you just write tf.data.experimental.autotune, and it will try to find the optimal like the values. So epoch by epoch, you will suddenly notice your program is actually getting faster. And maybe by the 20th epoch, it's getting much, much faster. So that would be the recommended way, where it's running through its own optimization functions and coming up with this fun value at the very end. I'll also say that, how in Gmail, you have some early exploratory functions which eventually become production functions. In a very similar way, TensorFlow also has these early experimental optimizations. They're usually tested, but before going to production, they usually are in experimental optimization side. You can turn them on, and maybe for your particular case, it can go fast. So you just have to turn these things true. And if I now join the entire story, this is my entire training pipeline, like the data reading pipeline, which is high performant and which will quite possibly be trying to become as efficient as possible. So we started with a few lines and just kept adding them till we became fast. So if you have a camera, take a photograph of this because this is all you need to become quite efficient, right? Now, I lied because you can do more. Like for example, with data augmentation. So when you use, Keras, you use OpenCV, Pillow, or any of these for augmentation, your CPU, turns out all of these sadly actually run on your CPU, not on your GPU. So you're still dependent on your CPU to read the files and then augment them, do all that drama, change the colors, and then feed it to the GPU. And believe it or not, that can be slow, right? So what can we do to improve the speed? The idea being that, can we do these augmentations in the GPU itself? Yes, you can. So instead of using the built-in augmentation functions like in Keras, for example, go ahead and use tf.image. So in tf.image, let's say you wanted to change the color, change the hue, change it, rotate it by 90 degrees. You have these inbuilt functions that you can use, and instead of using the CPU, now it uses the GPU. Good idea. Will become faster. That's good. But there is one slight problem, that it still has a limited number of functions for doing augmentations. So you get the speed, but the amount of things you can currently do are low. So hot tip, if you want to become famous, contribute it and basically make it equal to all the functions in Keras augmentation, and you'll be famous. That's what I will say. Alternately, another idea might be to use something which is already doing all this stuff for you, and that's called NVIDIA DALL-E. So it's available for multiple deep learning frameworks, whether you're using PyTorch, whether you're using TensorFlow, What this does is all the slides that I showed so far, it will basically build an entire pipeline to read the data as well as to augment them in one flow in a few lines of code. And the more interesting part is that, when you read a file, it's a JPG file, you have to decode it. It will actually decode the file hybridly in the GPU itself. It will resize it in the GPU, it will augment it in the GPU, and then it will train it in the GPU. And that makes it really, really fast. To give an idea of how fast it goes, NVIDIA used it to break the industry benchmark by training ImageNet in 80 seconds. 80 seconds. So that's the take-home message, that this might be another way you can use, especially if you use PyTorch and others, to become as fast as possible. And that's great. So now let's come to the meat of it, which is training. This is where the data reading part can actually have the maximum impact with the fewest lines of code. And these are like items in a checklist that you can follow. You don't need to remember them. But the training ones is where you then start getting into, okay, you can have better design into how you feed the data, the kind of weights you store, the kind of training methodology you get. So it goes a little to the next step, but you can take it, make things even better. So the first thing I'll say is TLDR, put this line at the top of your program and notice how your program might become 2 to 3 times faster. That's all I'll say. Okay, explanation time. So when you train a deep neural network, it's usually 32 bits. Now you might say, hey, Carl, if you reduce this down to 16 bits of weights, math should happen fine. And at the same time, the weights would take like half the size. And that's a really good argument. So we can do that, which is use half the size. Now, if we do that, turns out in inference that works perfectly. We can still get almost 100% the accuracy. In training, weights get a little bit unstable when we start to do that. So previously, this used to take a ton of code to get this to work, to train in 16 bits. And then eventually it turns out that you have to maintain a hybrid way where you have to save some sort of a master copy in 32-bit floating point, and then perform the forward-backward passes in 16-bit floating point. And then after each training step, we would then have to finally scale it back to 32-bit. So it was like, it's a hybrid mechanism, and this is called it's called mixed precision training. And now you have something called AMP, which is automatic mixed precision. And in automatic mixed precision, they do everything for you. And all you got to do is write that line at the top of the program, and this thing should just work out. If you especially have the newer NVIDIA chips, for example, with the Tensor cores, by newer, I mean in the last 2 years, I think you'll see the biggest performance difference. Google did some huge benchmarks, I believe for BERT or for translation, and they saw huge speed ups there too. The second thing that you have a lot of control and done very easily is figure out the largest batch size before you crash your program. All right, so usually you might have seen when you train programs, people use batch sizes of 32 or batch sizes of 64. So it's like you load 32 images at the same time. You don't load 1 million images at the same time. What you do is you take a small chunk that you can load in the memory, and you train for that 32 images, then another 32, then another 32, then another 32, right? So I have built a graph here which I vary the batch size, and then I show the GPU utilization in this red line. And as you might notice, when my batch size was like under 5, I was barely using 20% GPU utilization. When I went to 10, it increased. When I went to 50, it increased to 40%. By the time I started to reach over 500, my GPU utilization started to plateau around close to 85% mark. Keep in mind there's a log scale. And then finally it reached, I think, about 85% at the end till my program crashed. So that's why my numbers are till here. And at the same time, look at the blue line. And it shows that when my batch size was 5, it was taking me over 100 seconds to train. And by the time I was over 500, it's actually taking less than like about 1 to 2 seconds to train. And that's the point. You want to maximize your GPU utilization, and that's how it will become faster. But it's not just that you're maximizing the GPU utilization. GPU is getting fast, but like the overall performance of your pipeline will also increase in a more multiplicative factor, as you'll notice. So try to find a number 1 before you crash. More specifically, like in that 32 multiple before you crash. So that's a good thing you can do. So go for it and just tune it once. Number 3 is whatever numbers you use in life, make sure they are multiples of 8. So first came if you look at this graph here, this is a graph where NVIDIA was trying to train with different batch sizes, maybe trying the stuff that I was doing in the last slide. And they noticed something funky. When they used an odd number versus they used some even numbers, they saw like a multiplicative 5x speed up. 5x speed up. Actually, I should say 5x slowdown also in a different way. And then they also took some other even numbers like this one here, and they still observe the same 5x speed up or 5x slowdown. What's happening behind the scenes? So, first came the CPU, then came the GPU, and then came more specialized hardware like Google's TPU or NVIDIA's Tensorboard. And these are specialized accelerators. They are built for doing that mathematical multiplications. And to maximize it, they have some fixed sizes. And they have some minimum requirements. And some of those minimum requirements are like they need to be divisible by 8. To be more clear, the number of channels in your convolutional filter needs to be divisible by 8. If not, you won't get that speed up. The number of neurons in your fully connected layer of the variant needs to be divisible by 8. Similarly, the size of the mini batches needs to be divisible by 8. If not, instead of using that specialized tensor core, it will instead back up to the GPU. So it'll still train okay fast, but it won't be as fast as the money you paid for your hardware. So let's look at, that would be something that I would recommend. More specific recommendations, if you use NVIDIA's GPUs, use multiples of 64 or 256 for the optimal performance. And if you use Google's TPUs, use multiples of 128. All right, just remember that. Awesome. Another thing that's still in your control is the optimal learning rate. So learning rate is the one parameter which can basically decide the speed of your program or the fact that will it even converge to the optimal. So usually during deep learning training, you're trying to find that minima, which is the best possible value amongst thousands of dimensions for your whatever, the weights that you're trying to train. That's the high level idea. And the learning rate is really telling, what is the step size it needs to take to reach that optimal. Now, if you take really small step sizes like baby steps, it might take an eternity to reach that optimal point. If you instead take really large steps, quite possibly instead of getting to the minima, you might just overstep it and not even converge. So we usually need like the optimal value to get there. And I think this can take a long time to fully explain, but the shortest thing I can tell you is use this thing called Keras LR Finder, which implements a paper called Cyclic Learning Rates for Training Neural Networks by Leslie Ellen Smith. And what this will do is it will experiment on multiple number of values to come up with the value where the rate, we're trying to basically find a value which has the greatest decrease in loss. So the best learning rate is the point which has the greatest decrease in loss. And this will, in about, this is technically 4 lines of code, will find that value for you. So just take my, I think this can go quite long, so just go for that. The last thing that, so these things were parameters that are still in your control, but here's something that might be literally writing about 10 characters. The idea was that when TensorFlow 1.0 came in, you could compile things like a graph. And when TensorFlow 2.0 came out, it got something called eager execution by default. So you know how in shell script, when you write shell script, it runs it line by line. And then when you write a C program, it compiles the whole damn thing. and that's why C is fast. In a similar way, TensorFlow does some of this, graph-based running, but there are opportunities when you can just effectively just tell it that, hey, run this thing in a graph mode. When you have uh, some pieces of code which are small enough that they can get accelerated by it, it shows a lot of value. So all you got to do is write this word @tf.function on top of your functions. You define functions, just write @tf.function, and you will notice that on some of these functions will it lead to like really fast speeds. So here's a very simple example. Here it shows that here is a small function, with one convolutional layer. And I just copy that same damn thing, but just write tf.function on top of it and run it and time it. And what we notice is that there is a 10x speed up because this has been sort of compiled in the graph mode. And we notice a 10x speed up by using tf.function. So that would be one thing that I will recommend for you. Lastly, here's something that you can use. It's not a piece of code, but this strategy you use in training. So imagine that I tell you to learn French, right? And I give you two options. The option number one is that I'll give you a full French dictionary to learn and mug up. And then you go over all the words one by one and learn it. That's one way. The other way is that I show you the top 50 most common French words, tell you to learn that. And once you're done with this, in the next few days, once you start getting comfortable and you start to get a little bit egoistic, testy, we'll tell you, okay, here are 100 common words, start learning them. The moment you start getting better at 100, then I show you 200, 1000, and start to increase your learning, so you get maximum bang for your buck. And every time you get confident, I try to bring you to more realistic world. And I don't have a term for this because I have not seen it in literature. So I just call this overtrain and then generalize. And the idea is basically you overtrain based on some data, get it to be confident. And when it gets too confident, then you start to show it more data in different ways. Some examples being, how about, let's say if you're training ImageNet, instead of training on 1,000 classes, why don't you just train it on 10 classes first? You train it. When it starts to get confident, you then remove the last few layers and then put a new layer and then start to train it for 20 classes. So you're basically doing transfer learning then on 20 classes. When it gets good, then transfer learn on 50 classes, 100 classes, 200 classes, then 1,000. Right? So step by step, you get better. Similarly, when we augment data, don't augment in the first go. First, what you do is you just train data as it is. It will probably overtrain, and that's fine, but you'll actually start to converge faster. And then you gradually start to shake it up and increase let's say the rotation by 10 degrees, and then when it gets better than 20 degrees and more. Similarly, Fast Start AI by Jeremy Howard has this concept called progressive resizing. So imagine if I give you an image, and I just reduce the size by half in height and half in width. Now, this area of the image basically becomes 75% less. So when you train it, you effectively get a 4x speed up. Well, similarly, if I reduce the size of the height by 1/4, width by 1/4, I will effectively get a 16x speed up. So why don't I just train it initially with that 1/4 height, 1/4 width to know even if my things is even training, right? And then when it gets good, then I increase the size to half height, half width, and then I increase it to full height, full width. And if you start doing that, initially the program will be forced to learn higher level features, broad shapes, broad colors, and then eventually it starts to learn the finer level details when you increase it to full resolution. And that's a good training strategy. Last quick things I will say is, we have done all this great stuff, but you might still be using an inefficient program, the TensorFlow version you are using. When you do pip install TensorFlow or pip install TensorFlow-GPU, it can get slow. So what I will quickly say is try to either build TensorFlow based on the instruction set of your machine with right, it will give you something much more faster, because TensorFlow is usually built all the way from Raspberry Pi to a supercomputer. So use something which is better for your machine, or if you don't want to do all that and figure out instruction set, just use Conda. When you use Conda, it usually automatically finds the version best for your machine. For example, on Xeon CPUs, it will install MKLDNN version of TensorFlow, which can give 2x the speed up on the CPU machines for inference. That would be a good idea. Similarly, well, if you're on that thread, can we do multiple parallel threads for your TensorFlow program? And this is in general. So what you can do is set at the top of your program the number of threads equal to the number of CPUs on your machine, and you'll see the speed up. In a very similar way, you can do exploit parallelism within a single operation and set this particular parameter and see your number of speed up going fast. Now, to end it up, all things we saw so far was like using your Mr. Bean's car and trying to make it fast. But to end it up, maybe your program is as efficient as possible already, and you are still slow because the amount of time it takes to train. Maybe you're trying to train ImageNet on a normal laptop. This might not work. So maybe it's time to tell your boss that you want to buy this, $400,000 bad boy, NVIDIA DGX2. It consumes the power of 7 air conditioners, and if you like going to the gym, this weighs about 300 pounds, so that might be good exercise. Now this is $400,000 and has 16 GPUs, but just 2 weeks ago, NVIDIA came out with this chip, the A100 chip, and the basic system with one of these chips costs about $200,000. So you can decide, what you want to go for. Or you can take the advice of my friend who always says,
work with me here. The more you buy, the more you save. That's right, work with me here. The more you buy, the more you save. This is not a complicated talk.
So you can get multiple GPUs within the same machine, or you can get, on a cloud, you can just rent out multiple virtual machines. So before I go to the question and answers, I'll just quickly say, in TensorFlow, you can scale quite linearly based on even if you have multiple machines with just using 2 of these lines of code, at top of your existing program, and you can distribute training. Or you can use Harvard, which is from Uber, to distribute training amongst multiple machines. To end it all, we are discussing all these methodologies to become faster. But you might think that, hey, the real people who will be fast will be the Googles and the Amazons and the Microsofts of the world, which is true because they have resources. But don't underestimate your power. We could go to Dawn Bench and see that people are competing on training ImageNet with the cheapest amount of money. So somebody trained ImageNet in $7.43 by just using cloud machines. Right? Somebody used in under $20 using the Lambda GPU cloud. So you can train it effectively within $20. So you can go here, click on the source code and see what did they do that you can replicate training ImageNet within $20. Right? And all the money you save, you can use it to get the next bonus in your company. There's another competition on Downbench on who can train it the fastest, and people have been training it in 2 minutes. So just find the best benchmark, copy it, and then basically you start getting, best performances. Of course, you might not be able to beat Google and NVIDIA, who are using almost 1,000 of their TPU accelerators. But or last week, OpenAI came out with GPT-3, which behind the scenes was actually using a supercomputer from Microsoft, which was all rented out. So either you join these companies and get access to these, machines. So I'm gonna end my slides there. I'm probably gonna skip on the inference section, which is equally fun. But I will simply say, I hope by using these simple tricks, you are able to make your things fast. And if you need the slides, it's pretty simple. You just write the word wget presentation to this email address, practicaldlbook@gmail.com, and you'll get the slides for it. So you can start copying it and playing it in your own machine. And yeah, by the way, just to be clear, I have a checklist that you can print in A4 size sheets and start using it in your day-to-day job. Thank you.
Great. Thanks for the talk. And let's move on to the Q&A sessions. And there are quite a lot. If you can click the Q&A, open up the questions. Let's go through.
So the first question is by Ben. What do you think of OpenCV versus TensorFlow versus PyTorch? OpenCV was cutting edge in the past, but its documentation is really poor. Is it a viable option, or should we just stick to TF? So yes, OpenCV does have a DNN module to be able to run deep learning programs. But just looking at the ecosystem of TensorFlow, it's obviously the biggest. PyTorch is already stable. I think we are not living in the age where we would decide between TensorFlow and PyTorch. You have ONNX, which is like the model interoperable format. In fact, if you use ONNX, there was recently a thread where they're training on Hugging Face's transformers, and it was able to speed up the training by 2x the speed by using it behind the scenes. So my general advice is, use whichever framework, but if you just figure out how to use it optimally, it makes it fast enough. But the question really comes is at the very end, like which ecosystem gets you the maximum deployability in production at the end of the day. Luckily, we are living in a pretty mature state where whatever you choose is going to be okay. But TensorFlow versus PyTorch is going to be your general choice, to be honest. All right. Do you have these advices for PyTorch as well, or for vanilla Python? Great question. So you can actually look at how to make general Python more performant. But if you just use these tricks for TensorFlow, you can find the equivalent for PyTorch itself. Now, the things I was talking to you in training were very generic, right? In PyTorch, you have AMP, you can change the batch size, you can change the learning rate, you can change all those strategies equally. So similar learnings have been found in PyTorch also. You just have to find the particular commands for it. Usually when companies try to make things stable over time, they learn how to make things fast. So this has been done. So should work out. You can take the sheet that I'll send you and just, do it for that. So great question, Neo from London. Does the AMP take up performance due to back and forth conversion and maintaining multiple copies? Great question, Neo. Answer should have been yes, but sometimes like you do something which has a slight overhead, but the actual long-term value you get is much higher. That's the point. Just by doing this overhead, it's actually very little compared to the amount. You almost double the amount of memory bandwidth that you can get by doing that. And the speed up you get is much higher compared to the small amount of overhead. So yes, there is overhead, but in the long run of things, it just makes you faster. And again, PyTorch or TensorFlow, this should just work equally with one line change there. So the only thing you want to know is never do that yourself by hand, like code it everything by hand, just use that one line is what I would say. So thank you for the question. Next question is by Ben. What affects training crashing at high batch size? Great question. So imagine you use like MobileNet V2. I think it's like 15 MB. Now, when you use one image in memory, it will take 15 MB. If you use two images, that's going to take 30 MB. If you use 100 images, that's going to take 15 into 100. I forget whatever number that is. So on my particular GPU, I was able to fit in about 800 and something images before my 11 GB of virtual RAM in my GPU basically was finished up. So you're really trying to find how much memory you can feed inside your GPU for usage. So that's the real question. And that's what really affects. You can try it in Colab, what number you'll get, as well as on bigger machines. So that's great. Next question. Thanks, Ben. So the next question is, you have been focusing a lot on raw performance here. How does your changes affect accuracy, in particular the batch size? Great question. So ironically, the smaller the batch size, it actually acts as a regularizer for training, because by training from lesser number of things, you wobble through so much that it acts as a regularizer. Whereas when you go too large, you start to average a little too much that your training accuracy might, your training time to get to accuracy might slow down. So often this comes with playing with things. But I will say that there are techniques like LARS, L-A-R-S. People these days are training with 8,000 batch sizes commonly. Uh, in fact, people are commonly now starting to train with 80,000 batch size. So using large batch sizes with a proper optimizer will work out. But for most normal training occurrences, 256 to 512 should be fine. Again, you experiment, you learn, and you implement them. So that's what I would say quickly. Thank you for the question. Neo, again, it would be great if a small library or package could enable disable all these using high-level options. Great question. Maybe an opportunity for you to get famous. I will generally say that people focus on one thing at a time. It just happened that not each one of these tips was written in one place, and I was just following them. So I happened to compile them in one place and then ask people in multiple companies what tips they were using and just compile them. So these things are available. The only thing is that not every tip will cause you to be fast because maybe that's not applicable to your data set. So that's where you get your paycheck out, and bonuses more importantly. Do you know of any such packages, libraries? So yeah, I think I've mentioned a couple of those names, but these are for like one item at a time. Like Keras LR Finder was one example, and yeah, when you look in your crystal ball, okay, do you see any AI accelerated technologies to watch? Maybe Cerebras, FPGAs, others? Yeah, you actually already named. Any company Intel is trying to acquire, I think, is usually the answer for where things will be going. There's a conference called as Embedded Edge, and usually it's a more hardware specific. Most of us don't usually get to see that word. But the usual idea is that, like if you look at the sponsors who are sponsoring there, you can try to see where hardware is going, so your code can then eventually in future be ready for it. So that's where I look for places. So thanks for asking, John. I will go to Ben, who asks, can I train and optimize a model in Python into a saved model and expect the performance to be relatively good on edge devices too? Are there any gotchas and vary? High five. I think I spent 7 years on that. So it's not a problem of how you save it and load it. It's like, is your model performant enough? So you take your model, it's 32 bits, right? And the trick these days, if you really want to run fast on an edge device, is you reduce it down to 32 bits. I'll just very quickly show. You want to reduce it down to 32 bits. Yeah. And you can still get 98% the optimal accuracy. If you reduce it down to 4 bits, you can still get about 81% accuracy. But really the money is if you can reduce it somehow down to 1 bit. And if you do it like, just reducing it down, you're not going to get much of the accuracy reduction. But instead, if you use a technique like binarized networks, which reduces 32 bits to 1 bit networks, which is the proper technique, you can get almost, maybe 15% accuracy reduction, but you'll start running 60x faster. 60x faster. So a company did that. It's called xnor.ai, and they got acquired by Apple for 200 million. And sadly, you cannot use the code anymore. But good news for you, search for ELL. ELL, that is Embedded Learning Library. It's an open source library from Microsoft. It's built for makers, for hardware people, where you can use it and basically start to run your things, much, much faster. So I have a chapter on building robots in my book, which is for IoT devices, and you can actually, it has some of these techniques mentioned in there. So thanks for asking, Ben. Then the last question is between Neo equal to Mani from London. Hi, Mani. Sorry for not calling you before. Thanks for all the questions. Alrighty. Then one of the questions is from Mani. Do you also have TPU related tips, just like you shared for CPUs and GPUs? Great. So if you use all the things I mentioned, it should just run well on TPUs too, because it's still using the TensorFlow pipeline. So you are golden already there. So it should work out. Do you mind sharing the slides as well? Yes. So if you just email this wget presentation, it's a very developer way of doing it. You should just get it at practicaldlbook@gmail.com. So thanks for asking. Yeah, you will get the, I have to set up the email thing, but yeah, Ben, you'll get the slides soon. So thanks for asking. I have answered most of the questions. There's one question. Can I train and optimize a model in Python into a state model? Oh, that's also answered. And it looks like most of the questions except one from Ben. Awesome presentation. That's amazing. Thank you. Appreciate it. I hope you had a great session, and you keep tuning into many of these weekly sessions that I tune into at AI Camp. Just fun learning. And I'll just give two shout outs to two people. I'm mentoring a team at NASA FDL, which is Federal Development Lab. And in Feb of every year, we are looking for AI folks who can come and work with space scientists for 2 to 3 months in the summer and basically find something new in the scientists. Some of my colleagues like Siddha Ganju here, she worked with the team and ended up finding and discovering comets and meteor showers by using AI on something which was a normal thing. So if you're interested, search for nasa.ai. And I would highly recommend developers here to apply there and see an opportunity there. And to friends from Carnegie Mellon who are building the robo race car for tuning in. So hopefully you have